Good morning, everybody, and good evening, everybody, and welcome to my talk, which is about seeing trees in networks. Now, Silenia are a genus of flowering plants with a complex evolutionary past. In an attempt to shed light into that past, Pop et al. Generated a number of gene trees, two of which you see on my slide here. The one to the left is the RPD2A tree, and the one on the right is the RPD2B tree. Based on these two trees and a number of other gene trees, they then hypothesized the evolutionary scenario depicted in the middle of my slide for the taxa under consideration. Now, in a follow-up paper by Lott et al., together with one of the co-workers of the Pop et al. Paper, these gene trees were revisited in a different context. Now, what you see here on my slide is the tree on the left, which was the tree on the left of the previous slide, and the tree on the right, which is the tree on the right of the previous slide. In the middle, you see simplifications of both trees, where the tree in C is a simplification of my tree on the left, and the tree in D is a simplification of my tree on the right. Now, it should be noted that neither the tree in C nor the tree in D is a phylogenetic tree because, for example, the tree in C uses the leaf label S more than once, and the same holds for the tree in D. Now, as it's easy to check, the tree on the left, the simplified one, induces my red tree on the left here, and the tree on the right, again the simplified version, induces this tree here in blue on my right. Furthermore, the evolutionary scenario proposed by Pop et al. Can be redrawn in terms of this graph here in the middle, which only differs from the Pop et al. Scenario by replacing the label SO by a cherry, because S and O are two distinct taxa. Now, this structure in the middle of my slide is what people usually call a phylogenetic network. Now, for the purpose of my talk, a phylogenetic network on some set X of taxa, in my case Silene taxa, is a rooted directed acyclic graph with leaf set X, such that no vertex has in degree and out degree 1. The root has in degree 0 and out degree 2. Every leaf has in degree 1. And finally, every vertex that is neither the root nor a leaf has degree 3. For representation purposes, we also will say that if I have a vertex with in degree 2 and out degree 1, then we call this vertex a reticulation vertex, or sometimes people also call it a hybrid vertex. And if I have a vertex that is in degree 1 and out degree 2, then this vertex is generally referred to as a tree vertex. Now, as is easy to check, the blue tree is displayed by my network, whereby we mean the following. A phylogenetic network displays a phylogenetic tree if the deletion of all but one incoming arc of every reticulation vertex of my network results in a graph that is isomorphic to a subdivision of my tree T. On the other hand, the tree in red from my previous slide is not displayed by my network. The reason being that the tree in red uses the incoming arc of the parent of my cherry SO twice. Now, in order to understand what's going on, we have introduced the notion of a display map. And the definition of such a map is given here. And what it says is that a display map has to satisfy 4 properties. Firstly, it has to map every leaf in the tree to the corresponding leaf in the network. Furthermore, every vertex in my tree has to be mapped to a tree vertex or the root of my network. Next, every arc of my tree has to be mapped to a directed path that contains at least one arc of my network. In other words, we are not allowing paths of length 0. And finally, for any 2 arcs in my tree T, let's call them A and A prime, such that they share a tail. The first arc of A under my map psi must be different from the first arc of A prime under psi. Now, display maps are very similar to weak embeddings, Sensu, Irzel 2020. And both these concepts, i.e. weak embeddings and display maps, are very closely related to the concept of weakly displaying introduced by myself and co-workers in 2016. Now, the notion of a display map is not strong enough to understand or control what's actually happening. This is exemplified by my example on this slide. I have a network on the leaves 1, 2, 3, 4. I have a functionality tree on the left in red on these leaves, and I have a functionality tree on the right on these 4 leaves. Now, in order for the network to display my tree on the left-hand side in red, I have to use the outgoing arc of my hybrid vertex twice, and the same holds for my blue tree, which means this arc, which is the outgoing arc of my hybrid vertex, is used 4 times. Now, in order to control how often a arc is used or how often I'm going through a hybrid vertex, we have introduced the notion of rigidly displaying. And we say that a network rigidly displays 2 trees T and T prime if we have display maps for both of them, such that as an overall sum, I'm going through a reticulation vertex at most 3 times, and for each parent of a reticulation vertex, I'm only going through that vertex at most twice. Now, intriguingly, if I make a small modification to the network that came from the Pop et al. Paper, i.e. if I look at the network as displayed in my slide here, then that network displays, as defined above, my tree in red, and it also displays my tree in blue on the right here. So what is going on? Now, the key to answering this question is held by 2 concepts, tree child and temporal. And for completeness sake, I have included both definitions here. We have a phylogenetic network, and such a network is called tree child if every non-leaf vertex has a child that is not a reticulation vertex. And it's called temporal if there exists a map from the vertex set of my network to the non-negative real numbers, such that for all arcs uv in my network, the value assigned to u and v is the same if v is a reticulation vertex, and otherwise the value of v has to be strictly larger than the value of u under my map T. Now, the network here, which is the redrawing of the Pop et al. Network, is in fact tree child. Now, the observation that we have these 2 networks is not a coincidence, because we have the following result. We have 2 phylogenetic trees, then we can show that these 2 phylogenetic trees are rigidly displayed by a temporal tree-child network if and only if they are displayed by a temporal tree-child network. What is important to note, though, is that the temporal tree-child network referred to in I need not be the same as the temporal tree-child network referred to in assertion number 2. Now, in fact, a more general result or a stronger result holds. Again, suppose we have 2 trees, T and T prime, they are phylogenetic trees, then the following statements are equivalent. These 2 trees are rigidly displayed by a temporal tree-child network if and only if they are displayed by a temporal tree-child network as said on my previous slide. However, this is equivalent to there being a cherry-picking sequence for TNT prime. Now such sequences are certain leaf operations as introduced by Humphreys et al. In 2013, or there is a fork-picking sequence for my two trees. Now fork-picking sequences generalize cherry-picking sequences, and they are introduced in the archive paper I mentioned before already. Now, due to time constraints, I neither have enough time to go into the details about the proof or tell you much about how a fork-picking sequence, or in fact a cherry-picking sequence, is defined. However, if you're interested, then please feel free to send me a quick email, and I'm more than happy to explain to you these two concepts and also give you details about the proof. Finally, many thanks for listening, and goodbye.